Okay, so welcome everyone to this lecture. So far we have seen empirical risk minimization and the framework of regularization. The summary of the discussions that we have had so far is that by changing the loss function and the regularizer, one can impose certain type of behavior in the hypothesis that we are looking at. So that is the moral of the story so far. You change the loss function and you impose a particular type of regularizer on top of it. The kind of classifier or the hypothesis that ERM outputs will be different. So this is the general philosophy of how ML algorithms are designed. Regularizers can come in multiple forms, right? One, you change the architecture, or what do you mean by architecture? The class of functions that you choose from to build the hypothesis is your architecture. You can change that, or you can add an explicit regularizer in terms of a constraint in the optimization problem, or you can perturb the data with some noise and so on. And there are multiple ways to add regularizer. But the fundamental idea is that if you want to observe a particular type of behavior in your hypothesis function, you change the loss function and or regularize. Right? When I say regularize, it also means that you change the architecture. Changing the choice, making a different choice for the hypothesis is also a regularization, as we saw. Right? So pick a classifier class, pick a class of functions which will form the hypothesis space. Within that space, you solve an optimization problem with a loss function by adding regularizer, and you add different regularizers, you choose different hypotheses, different kinds of behaviors are seen. That is what we have seen so far. So we will continue this thesis, okay, and look at many other choices for the hypothesis function. One significant choice that is made is these class of functions called neural networks, which we will see later. Now, for the sake of completeness and the elegance that this particular algorithm brings in, we will look at these classes of hypothesis which are called Max-Margin classifiers, okay, of which support vector machine is a member. So support vector machine is an extremely elegant way of formulating hypothesis function. In fact, remember in the beginning initial lectures I told you that one of the central problems in machine learning is to relate the minimizer of the true risk with the minimizer of the empirical risk, right? Support vector machine gives an elegant mathematical formulation of actually bounding the empirical risk in terms of bounding the true risk in terms of the empirical risk. So these classes of results are called sample complexity results, where the true risk, okay, is bounded as a function of the empirical risk and the number of samples that are used for the training. Now that was a very strong result, because one question that often gets asked is that how many samples do you need in your data set to achieve a particular accuracy, right? So this question is a question on true risk, because if the question were of empirical risk, then we already know the answer, because we can overfit on the data that we are given. But the actual question is, what can you say about the true risk having performed an ERM on the data that you have been given. So if there is a result that relates the true risk with the empirical risk, that is a very strong result, right? And support vector machines is one class of algorithms that actually gives a bound on true risk in terms of the empirical risk and the number of data samples. However, that is why it is so powerful, right? In the sense that you can theoretically guarantee that your algorithm is going to have this performance on unseen data as well. But unfortunately, what happened historically is that these algorithms did not perform very well on very large scale data in high dimensions. That was an empirical observation that was made. And for the kinds of algorithms or the hypothesis functions that are used today in modern ML, which are neural networks, you cannot come up with sample complexity bounds such as SVMs. So that's why the question of what is the number of samples that are needed, and can you give a theoretical guarantee on what would be your performance, what would be the performance of the classifier based on neural network on unseen data, cannot be theoretically answered today because of lack of such sample complexity bounds for these kinds of transformer based models. However, SVMs do give such a kind of nice formulation. So I mean, in today's scenario, max margin classifiers or support vector machines are seldom used in practice, right? But this philosophy that by changing the loss function and placing a very nice regularizer, you can impose a good behavior on the classifier is what the take home message is when we look at max margin classifier, and for that sake we will look at the max margin classifier in its entirety for a couple of classes now, right, and then before we move on to the neural networks. Okay, so let us look at max margin classifiers or support vector machines. Okay, so let us consider a binary classification problem to start with. I will start with the simplest of the formulations and then we will keep on increasing the complexity. Consider a binary classification problem. So we have X data that is in RD and Y. We have been using symbols 0 and 1 to denote classes so far. Here I have used -1 and 1 for a particular purpose. You know, algebra will become easier if I use -1 and 1. Does not matter, as you know, right? I mean, these are just two symbols. So let us say that the output classes are -1 and 1. Okay. Now let me introduce you to a concept called discriminant functions. See, the recall that for some cases of class conditional densities, the classifier will take this particular form, right? So there will be, it will be 1 if I had asked this as one of your questions, right, in your exam, that for a particular case of class conditional density, a binary classifier or the optimal classifier will take this particular form, okay, where g of x is some function of x, right. So it's actually you have this to be a function from Rd, which is x, to R. Okay. And in the, okay, actually it's not for some cases of class conditional densities, right. In fact, can actually say that a binary classifier, any binary classifier can be represented as follows. Actually, this is in general. Any binary classifier can be represented this way, right. We used classes as 1 and -1, right. So we can take it as 1 and -1 here. 1 if g of x is greater than 0 and -1 otherwise. So this function g of x is what is called as the discriminant function. Okay. Now for the case where the class conditional densities are Gaussian, this discriminant function will become linear. There is no need why this discriminant function has to be linear in general, is any function, but for some cases this discriminant function will be linear, correct. So let me take an example. Okay, let me write that for some specific cases. specific cases of class conditional densities g of x will be linear. The reason I am talking about linear decision boundaries is that we will start the Max-Margin classifier, the formulation, by assuming that we have a linear discriminant function, and then we will generalize that to nonlinear discriminant functions. Okay. So, what do you mean by having a linear discriminant function? Let me show you an example. Suppose x is in R2, y R2, this is what I can write, minus 1 and 1. So, let us say that I have two classes like this. This is all x such that y is equal to minus 1, and this is all x such that y is equal to 1. So, what are these axes, by the way? These are axes of the data dimensionality. What was the symbol that we were using? Superscript, right? This is x1 axis and this is x2 axis. So, every x is of the form x1 comma x2, right? You have two axes and this is how the data is distributed. Okay. Now, in this case there is a discriminant function g of x. Let us write that. It is a linear discriminant function. This is g of x, that is equal to some w transpose x. Also add a bias term here, plus b. So, this is an example of a linear discriminant function. So, finally the classifier says that if my x is on the upper side of g of x, then it belongs to one class, and its lower side of g of x, it is one other class. What do you mean by that? There is a line, and if the data point falls above the line, belongs to one class, below the line one other class. And you understand what above and below is. So, mathematically speaking, all we are saying is that if when we compute this h of x, right, if for that particular x, if g of x is greater than 0, then I classify it as one point and the other. You saw an example for this in your exam. So, this is exactly what I had asked for in that first question, right. You have to show that under a specific condition you will have your classifier with this particular form where you have a linear discriminant function. Make sense, right? So, this g of x is called discriminant function, and if this discriminant function, you understand what a discriminant function is, right? So, there is hypothesis classifier. If the classifier decides based on a function of data, that particular function is called the discriminant function, and in a specific case where this discriminant function happens to be a linear function of data, it is called the linear discriminant functions. Okay. We will start our treatment by assuming that the classifiers that we have linear discriminant functions with it. So, that is the easiest way to look at it. Okay. Right. Now, with this, let me define another idea which is called linear separability. A data set D is linearly separable if and only if there exists a W and B such that W transpose x plus B is greater than 0 for all x such that for all xi such that yi is equal to 1 and W transpose xi plus B is less than 0 for all xi such that yi is equal to minus 1. You understood what is it, right? So, if there exists a linear discriminant function which would end up giving 100% accuracy on some data set, then that data set is called as a linearly separable data set. That's called linear separability. That you can always find a line, okay, that would give 100% accuracy on the training data or whatever data that we have. If such a data set exists, then that data set is called linearly separable data. Is that okay? So for instance, whatever I have drawn here is linearly separable because you can find a line that can separate this. Okay, so here is a question. Suppose data is linearly separable. How many discriminant functions can exist? Infinite, right? Yeah. So that is something that you should keep in mind because we will talk of an optimal discriminant function. So that is what we are going towards, right? So how do we come up with an given that there can exist infinite discriminant function, is there a way of defining optimality? Okay, that is where we go. But yeah, but you understand this, right? If data is linearly separable, then there can exist infinite discriminant functions. Okay. Okay. So let us now ask that question. Corollary is linearly separable data will have infinitely many discriminant functions. Question: is there an optimal discriminant function among all possible discriminant functions is the question. One can define optimality in multiple ways, right? I mean, Max-Margin classifier or support vector machine is one way to define optimality. So that is what we will look at. So given that data is, so now please note that in practice, data will neither be linearly separable, right, nor be even separable that way, right? So now the question is, even if you have a nonlinear discriminant function, can you guarantee that it is separable under any function is a question which need not be the case. So the most generalized version of a Max-Margin classifier does not put these constraints. No, it assumes that data is neither linearly separable nor separable under any other constraint, right? But for the ease of formulation, we will start with the case by assuming that the data is linearly separable, okay, and then we will increase the complexity of that. Okay. Now, right, let us consider optimality via maximizing the margin. Okay, let us look at this. Now, since, okay, so consider linearly separable data. Now, since it is linearly separable, so there exists an epsilon that is greater than 0 such that W transpose xi plus b is greater than epsilon for all xi such that yi equal to 1, and W transpose xi plus b is less than epsilon for all xi such that yi is equal to minus 1. What do I mean by this? Now, initially the way we defined our discriminant function is that if the data point is above the line, then we have then we assign one class, and if it is below, we assign one other class. Now we are saying this, there always exists a small epsilon, okay, within which you can push the decision boundary. Okay, by the way, discriminant function is also referred to as the decision boundary for obvious reasons, right? Yeah, you can push the discriminant function geometrically or decision boundary by an epsilon if the data is linearly separable. So what do I mean by that? So look at this, we will take a different color. Choosing color is an issue, okay. Do you see that margin? Should I use a different color or something? This is okay, right? Yeah. So this, right, is, what is this width mathematically? 2 epsilon. This is 2 epsilon. So width is 2 epsilon. I can always push this decision boundary within a margin of 2 epsilon at epsilon either sides. I mean, why have I taken it symmetrically? This is just for algebraic convenience. I use 1 epsilon. All I am saying is that if the data is linearly separable, I can always find an epsilon such that the decision boundary can be moved along. In fact, think about it. In other words, I am saying that there always exists a space within any decision boundary that you take within which there exists no data points, right? This is true for any linearly separable data set. Do you all agree with this? Okay, because this is a key idea, you convince yourself that this is true. Okay, so what does it translate to mathematically is that instead of writing my discriminant function as greater than 0, I can write it as greater than epsilon and less than epsilon for 2 different classes. Okay. Now, so now W and B can be rescaled. Correct. Thanks for that. Yeah, it should be less than minus epsilon. W and B can be rescaled, okay, such that now W cap transpose xi plus B is greater than epsilon. Sorry, greater than, not epsilon, now it is 1, and W cap transpose xi plus B cap is less than or equal to minus 1. Now once we have this epsilon, right, I can rescale W by dividing the entire thing by epsilon, okay, and rewrite the discriminant function in this particular fashion. Is it all right? Does this change the line? Does this change the discriminant function? Why? What is this W, by the way? I mean, geometrically speaking, it's the normal. The direction of W is the normal to the decision boundary, right? So rescaling it will not change the direction of that. Therefore, this W does not change. This line does not change. Okay, I can always rescale it. I will not write as W cap going forward. I will still write it as W because notationally it's easier. But you should know that we started from a discriminant function being greater than 0, and then we put that margin, and then we rescaled it to make it plus or minus 1. Okay, I'll continue writing it as W. Okay, don't get confused. Okay. Now this, why did I do all this, is to ensure that these discriminant function can be written in an elegant algebraic form, right. So now the above can be, so this is all for all xi such that yi is equal to 1, and for all xi such that yi is equal to minus 1. Okay, I just want to combine this. So above can be combined as, just write it as Wi times W transpose xi plus b is greater than or equal to 1 for all I. That's it. We did all this to ensure that I can write the discriminant function in this particular way. So why is this correct? Look at this, right? If my Wi is 1, then it is W transpose xi plus b is greater than 1. If it's minus 1, then it is W transpose xi plus b is less than 1 or less than minus 1, right? So I can combine both these conditions this way, that's it. Does that make sense? We did all this. See, I told you that I assume my classes to be plus 1 and minus 1 for this particular reason. 0 and 1 will not make me write it this way. So started with plus 1 minus 1 and rescaled it so that I can write the classifier this way finally, discriminant function this way finally. Okay. See, what is the difference between the final hypothesis or classifier and the discriminant function? It's that you put a threshold on the discriminant function to get the final classifier, that's it. Remember, no, h of x is equal to 1 if g of x is greater than 0, that's what it is, yeah, that's it. Okay. Okay. So finally, for the linear separable case, there exists a W and B such that yi times W transpose xi plus B is greater than or equal to 1 for all I, right? That is what it boils down to. If the data is linearly separable, there always exists a W and B such that this product is greater than or equal to 1, correct? Also, there exists no data point between the lines or the hyperplanes. See, in 2 dimensions the discriminant function is a line, in higher dimensions it is a hyperplane, remember that, no? Between the hyperplanes W transpose x plus b equal to 1 and W transpose x plus b equal to minus 1, isn't it? If the data is linearly separable, I can draw 2 hyperplanes, W transpose x plus b equal to 1 and W transpose x plus b equal to minus 1 such that there exists no data points between them. Let us go back to our figure. So these are the lines that I am talking about. I think this is too dull a color to do this, let us use some other color. So this line is W transpose x plus b equal to 1 and this is W transpose x plus b equal to minus 1, and you see that there does not exist any data points between these two.
So can there be a point on the line?
Let's get to that in a while. So the question is, can there be a line on the point? They are called support vectors, as we will see later. So we will get to that, right? There can be, because the way we have defined it, there can exist, but between them there is no data point, right? So I mean, the take home message is as follows, that if the data is linearly separable, then you can always find the W and B such that for all data points the product of y times W transpose x plus B is always greater than or equal to 1, and there exists no data points between W transpose x plus B equal to 1 and minus 1 lines. Is this alright? Okay. See, remember, why are we doing all this? We still want to formulate this optimality of a discriminant function. That is why we are doing all this. Let us see how this thing is useful now. And by the way, okay, there exists no data point between these 2 lines, and both of these are parallel to, okay, they are parallel to what? The discriminant function, which is W transpose x plus B equal to 0. This is the discriminant function. they are parallel to this, correct? Okay. Consider the distance, perpendicular distance between the lines, and by the way these parallel lines are what are called as margins. Okay, I'll actually define margins in a more rigorous fashion in a while. Yeah, just use these are called margins. Consider perpendicular distance between the margin. What is it? Huh? The what if you have two hyperplanes? What is the distance between them in terms of its slope? It is 2 by norm w. No, they are parallel lines, and the distance perpendicular distance between them is 2 by norm of that. Okay. Now, one criteria for optimality of a discriminant function g of x is that this distance, no, is to be maximized. This is one way one can define optimality. So, amongst infinitely possible discriminant functions, give me the one that maximizes the distance between margins. Why is this a good criteria to define optimality? There are multiple ways to answer this question. So, there is a very nice learning theory way to answer this. Only if you do this, then the true risk can be upper bounded in terms of empirical risk. Okay, that is the best way to answer this question. Remember, finally our goal in ML is to learn, is to ensure that minimizing empirical risk, right, leads to a good minimization on true risk. So, if you do this, then you can show that the true risk can be bounded in terms of the empirical risk and the margin actually. Okay. So, the higher the distance between these two margins, the better is the bound on the true risk is one way to see it. And there is also a geometrical or an intuitive way to look at it, right. So, why do you want the distance between these two lines to be maximum? So, let us look at that. So, why do you think amongst all possible classifiers or discriminant functions, the one that has the maximum margin is a better classifier? Come again? Why? That's correct. I mean, I already told you that, right? I mean, it will have a better bound on the true risk. The answer that he gave is that on unseen data, the one that has maximum margin will perform better. My question is why? No, okay. So, see, I am not saying that the discriminant function should be between the lines, between the classes. The notion of between the classes is not even well defined. See, when you, okay, so this is one general piece of advice that I would give all my students, right. To me, personally, intuition doesn't mean anything as long as it is supported with evidence and math, because otherwise it's all fragile language. So, language is too fragile and you can't explain anything with language, okay. But even when you are drawing intuitions and inspirations, right, ensure that you use math to do that. For instance, I mean, there's nothing against what you said, but because you made that statement, right, what do you mean by between the classes? See, classes are the values that my other random variable y can take. It's only +1 and -1. So, now what do you mean by between the classes? I can understand what you mean by between classes. There is some cluster and there is some cluster center and all that, which we have not defined. Okay. All that we have defined so far is these two lines. We know what a discriminant function is and we know what margins are. Okay. Margins are these two lines which are parallel to discriminant functions such that there exists no data point between the margins. That is a well defined concept. Now the claim that I am making is amongst all possible, every discriminant function will have a margin, isn't it? I draw any discriminant function or decision boundary that is going to have a margin. The claim is amongst all discriminant function, the one that has the maximum margin will lead to a better generalization. Algebraically, the easiest way to show that is that my true risk, right, is bounded by the empirical risk that is scaled by inverse of the margin length. So the larger is the margin, okay, the tighter is the bound on the true risk in terms of empirical risk. That's the easiest way to say it, okay, and that convinces me completely because that's what my goal is. Now if you want intuition, I just want you to give me the intuition that why do you think the larger this distance is, the better its performance will be on unseen data.
Suppose that is a small distance, then a point if it falls below that line, but it may be actually in +1 plus. Because it is a small distance, there can be discuss.
Does it make sense? So what he's saying is, in fact, the discriminant function that I have written in this example is not the Max-Margin classifier. A Max-Margin classifier is maybe somewhere here like this, something like this, no? Okay, let me write that down so that you can compare both the classifiers. I am spoiled for choices, no? The alphabets, colors, run out of everything. Okay, huh? Red is already taken, no? Yellow does not, okay, blue is not taken. Yeah, blue is not taken, okay. So let us write another classifier. Okay, let us say that this is another classifier at margin. I have written the margin of the other classifier. Which classifier do you think is better, or which discriminant function is better? Is the blue one or the pink one? It's obvious, right? Why? It's obvious. See, it's obvious algebraically also. I can show you that the true risk is upper bounded by this particular thing. But now, why do you think this is better? Whatever explanation that he gave. So what happens is, if you have margin and the classifier is always here, right, in between these two lines. Now during test phase, test data points actually have this much of space to fall without giving up the, without making an error on the actual classifier. Now if this is small, what happens is if your data point falls outside the margin, or right within the margin, it has the chances of wrongly crossing the decision boundary. You understand? Did you get the intuition? So algebraically what's happening is, if you have a larger margin, okay, then you have this much of space, you know, the space within which a data point can fall without making a mistake is the margin, isn't it? During test phase, I mean, if it's suppose it is above the, as long as it is above the discriminant function, the class is correct, okay. However, during the, I mean, we have constructed the classifier so that anyway it is linearly separable, and when we do empirical risk minimization, we will ensure that we have 100% accuracy on the training data. So during test phase, as long as it is above the discriminant function, it does well. However, if the margin is higher, okay, it can fall within the margin without making an error or a mistake in classification. So the larger the margin is, the better the chances of generalization. Is this intuition enough?
Something falling in margin, why will this not be a misclassification?
Because the decision is taken, the question is, if something a point falls within the margin, right, why isn't it is misclassified? Because the decision is taken based on the discriminant function, not on the margin. As long as it is above the discriminant function, it is taken as one class. Remember, final decision is based on g of x, not on margin. And by the way, there is the textbooks, different textbooks use this word margin in different contexts. You know, there are two ways that people use. This width is referred to as margin. Okay, some books call these lines themselves as margins. Okay, yeah, so it depends on what book you are looking at. Either the distance between these two separating hyperplanes are called is called the margin, or the lines themselves are called, the lines that are parallel to discriminant functions are also called margins. Okay.
We are not sure if the true data will be linearly separable or not.
Agreed. So as I said, this is just formulation. So we will generalize this for the case where the data is not linearly separable. In the next class, what we will do is we will assume that the data is not linearly separable, and then we will look at what the treatment is.
And sir, if it is even linearly separable, if the true data is corresponding to a decision boundary which has a smaller margin, then how do we know that it's still
There is no true data here, right? See, once the data is linearly separable, you can come up with infinite decision boundaries. The question that I am asking is, amongst all these possible decision boundaries, which is the one that gives me the best generalization? What do you mean by best generalization? In terms of reducing the true risk. See, all we can do as practitioners is to minimize the empirical risk, right? The question that I am asking is, which classifier amongst infinite possible choices for the classifier is the one that minimizes the true risk the most? The answer turns out to be the one that maximizes the margin. That's it. Okay.
The hypothesis function for the base classifier is in terms of the class conditional. So can we connect between the
Oh yeah, if the class conditional density happens to be that Gaussian with same means, same variance, it will turn out to be a linear discriminant function, no? But will that, okay, so the question that you asked is, I understand your question as, suppose the data is let's say coming from a class, a true class, a Gaussian class conditional density, and we estimate the class conditional density perfectly, and the discriminant function happens to be linear. In that case, will it correspond to the Max-Margin classifier is the question that you are asking, isn't it? It is optimal. It is optimal in that sense. That's a good question. The question that he is asking is, will the optimal classifier that the base classifier that we get in terms of linear decision boundary, if it happens to be a linear discriminant function, will it correspond to the Max-Margin classifier? Not sure. That's a good question. Let me think about it. Because optimality, in terms of minimizing the true risk, right, will it always corresponds to maximum margin classification is the question. In other words, let me think about it. This is a good question. I will come back to this. Next class I will try to answer this. Okay, you got the question right. It's a nice question. Does maximizing the margin, okay, finding the discriminant function such that the maximum margin is maximized, always leads to the base classifier? I'll think about it. I mean, intuitively it looks like it should, but let me confirm it and then tell you. Okay, shall we move on? So now, yeah, one criteria, that's why I wrote one criteria for optimality. It's not the criteria. I mean, it would have been the criteria for optimality had it been the base classifier. So one criteria for optimality is that you find a discriminant function such that the margin is maximized. Okay, so let us formulate this now. We will stop here and continue in the next lecture.